Alright, welcome back. So I've got time for a very short one this morning. These are the most important ones to make, I would say. If you've got a little bit of time here and there, and you use it to make progress in something, that those little that's how it really adds up and you really get things done. So you're going to spend about 15-20 minutes here and keep reading the machine learning for network and cloud engineers. But moving on to use case 8, what log message is expected next? Pain point. Following our subseries of log-related use cases, we will look at the logs as a sequence. Logs arrive at our syslog server, and it is challenging to know if this log is expected. You might get a totally expected log based on previous logs that such a device has generated. Hence, it would not be a concern. You may receive, however, a log that may not be expected, and therefore a symptom of a new or different problem that requires attention. Logs are an ocean of information. There are many devices and many types of logs, and it isn't easy to make sense of them. How do we know if a log is normal or anomalous? How do we know if the log we just received is expected? While this is something you may not be wondering about today, it is a reality that there is a big gap today between what logs as a source of data contain in terms of information and what we, as users, usually extract and leverage. Multiple companies have done their business out of basic log processing and mining, trying to address this gap. That is the key pain point. In this particular use case, I would like to show you how we could help solving one of the questions above. Is this log expected or not? Approach. Logs are generated by devices because something happens to them. Depending on what happened to them, some logs will be triggered, either one or a series of them. Somehow, we could try to find out those patterns and predict what the next most likely log will be. Effectively, we are going to use NLP techniques to try to predict the next log, leveraging the logs we have received previously. We could take a sequence of the last n logs generated by one device and try to predict what the next log should look like given the past logs. Our approach will be a bit simpler just for compute resources reasons. We will take only the last log and try to predict the next one. Intuitively, we could argue that if we take various logs, we would be able to provide more contextual information to the model, which is entirely true. For practical reasons, when you take various logs using the detailed approach I will be describing, the matrices become very large, and training with the standard laptop or Google Colab resources becomes challenging. That is why it is good enough for this use case and the main goal, which is not to resolve the case optimally, but to illustrate and enable you to learn about these ML techniques. Therefore, the approach will be to predict the next log out of the previous log received. Let's give it a try and see how it works. The approach described in this case is based on existing public research. See 33 for reference. Input data. As in the previous use case, we are going to use SANS generated log data. We will be expanding the scope for log generation to all devices, and we will generate 5 hours worth of log messages. These log messages have been generated both based on the event policies configured, but also the incident policies in SANS that specify certain sequences of logs that need to happen when such incident triggers. This will somehow introduce more predictable patterns and sequences that could help a model to learn about them. In our case, as I explained, we are going to use only the previous log, so these sequences will be less useful. But anyway, we are trying to introduce such patterns so that we can work with models to discover them. The following are the incident policies currently configured in SANS. Alright, so this is data frame. We'll have to pull up a notebook for this use case, so I'll do that briefly. I'll do that in a bit. As you can see, there are only two incidents. Let me describe a bit of the logic that these policies convey. An incident policy entry captures the impact that this incident must result in a given entity, a device, or an interface. There is some flexibility on how to define the target entity. The impact can be in metrics or events. When it refers to metrics, we can express in the impact details field what should happen with the metric during the period of the incident. Take a certain value during a number of minutes, etc. When it is about events, we can specify a sequence of events that SANS should generate. For example, in the incident called hardware failure, we are trying to simulate a hardware failure situation in PE-57 that will happen every minute. It will trigger a hardware fault log event, and in parallel, a sequence of events like the following. We have a list that contains an event name, followed by a number, then another event name, followed by another event name, and so on. Effectively, based on this list, SANS will generate initially the interface optics fault event, which is a certain type of log message. Then after 0 minutes, it will generate an interface local fault event, another type of log message. After 0 minutes from the start, it will generate an interface down event, a log message. After 1 minute from the start, it will generate a BGP session down event, another log message, and so on. So we have specified a certain sequence of logs we want SANS to generate that somehow simulates the type of logs you may expect in this fake incident. While not perfect, it allows us to have control on what we want to generate. As I referred above, it introduces patterns that we can try to surface using analytics. Taking the above into account, we invoke SANS to generate the logs required for the period of 5 hours. So time delta there is 5. All right. Alternatively, as with all other use cases, there is a preloaded data set of SANS generated log messages, CSV file, log anomaly detection, etc. we can use, since the generation process takes a few minutes. Either way, we will get a data frame that looks like the following one. So events df. We have about 40,000 logs as our input data set. They are time ordered, so they represent the sequence of logs. Alright, and before moving on to problem resolution, you know what? Actually, it's probably, yeah, let's just keep going. We're still dealing with the notebook here. so I can go back and run it at any time. So let's keep going here. Problem resolution. As explained in the approach section, we will train a model to predict the next expected log from a particular device given the log we just received from a device. The results I have obtained in our notebook are not spectacular for different reasons. Since my goals are the rationale and methodology, not so much the results. So you can understand the process. The results I will show you at the end of the notebook are good enough. Given the data frame we have as our input dataset, cleaning it up from NaN values is a good practice, which will make our life more complicated later on. I will simply remove the lines containing NaN because dropping some logs will not significantly change the results in this case. You have to assess this on a per use case if dropping some data will or will not impact. And if it does, then you need to use other strategies to handle the NaN values. In the way SANS has generated the data, the source column does not truly refer to the device, but the entity for which it has generated a log. Sometimes logs refer to an interface, so the source includes an interface identifier. This is not useful for the analysis we want to do. However, there is a useful column called fields, which contains a good amount of information, including the device name field, which is what we are interested in. Since we want to understand the sequences of logs on a per device basis, the fields column is actually a string. We need to do some gymnastics with the string to split it in different ways and extract the device name data. You could use other approaches using regex, but I did what I found easier for me. Now we have a new column that clearly identifies the device that in our SANS simulated network supposedly generated this log message. Next, we have to start preparing the data for our subsequent analysis. We have a table of logs with logs from many devices interleaved, but we need to have a clear view on, given a log from a device, what is the next log we have received from the device. The answer is all in the table, but we'd better make it more explicit for our model to learn it. We will create a new column called next log, and we will navigate the table for each device to fill it properly. Alright, I think this is a good spot to get the notebook running. So we're on use case 8. Let's start a Jupyter notebook from here. Alright, and then go to use case 8. So an invalid notebook may not function properly. The validation error was this. So notebook validation failed. Additional properties are not allowed. Metadata was unexpected. So we've got an additional property to this notebook. So maybe we can clear notebook widget state. Interesting. I don't know what this means. So we live in the modern world, so let's ask ChatGPT. Alright, ChatGPT is having some problems this morning. Okay, so there's some cells there. Okay, so we'll get to that when we get there. I guess it just means that some of the cell output is causing that, so that'll be something to deal with later on. I should still be able to run it cell by cell up until the cell that's causing that issue. Alright, looks good. And then we've got to change the statement here. Looks good. Now this is the one that takes a while to run, so looks like things are good. We just got that future warning, so we gotta let this cook for a few minutes. So let's make some progress in the reading. Now data is starting to take the shape we need. However, given that we have combined a log with the next log received per device, there are always cases where one log was the last one, therefore there was no next. We have to remove those entries which are not informative anymore. We still have at this point logs as text strings, and that is not how a machine learning model can consume them. Remember, they need to be consumed in these numbers 0 through 1, these decimals, so that they can be. I mean, it depends on what you're doing. With a neural network, it needs to be. So we need to work on their numeric data representation. First things first, let's transform the data frame into two lists of logs. Lists or arrays are easier to manipulate, and ultimately we need to feed our model with an array of numbers. Yep, so an array of numbers. You also need if you're doing supervised learning, you need the labels, categories. Yeah, so one important point when dealing with strings, like in this case, the log messages, is that we need to standardize the length of the strings. The length must be the same for all sequences we feed a machine learning model. We cannot use variable length input data. Likewise, when dealing with images, a CNN convolutional neural network expects all images of the same size both in training and inference. So we need to adjust the size to what the CNN is configured for. In the case of text sequences, that means you may need some padding, either before or after, if the log specific length is shorter than the standard length we determine to use. Alright. And let's check back in on the notebook. There we go, we have a data frame. So, oops, and yeah, so we can write the data frame out, that's fine, but we want to be careful not to load in the preset one, and we want to use the one we generated. Now this is a warning, so we're good to go with that. Yep, so we can print out the data frame here. Looks good. And we've got our yep, so that's all working. Okay, so now here we've got a. Oh no, it's just a. Oh yeah, no, it is real error. So we've got the copycat warning, which is happening here on this. Looks like a temporary file, but then we have a real error as well. We have a type error. So this cell. Let's see what cell we're looking at in the book. So we're looking at max log length cell. So that is going to be the cell down max log length. Oh, that's going to be the cell all the way down here. So okay, so there's some kind of issue happening here, and as a result, we won't have. Yeah, I think our data frame's not going to look right. So here's the data frame. So let's see how that compares to the data frame in the book at this point. Oh, you know what? It's not going to show it yet. So yeah, let's just keep going. Hopefully that wasn't a big issue. And we'll see. We'll see if we get the same results. So we've got a length of a log list here. So we don't have any match. We don't have any output to see whether it matches or not. Everything else is continuing to run. So I'm out of time. So I think what I would like to do is just skip ahead and plot out this graph and make sure it looks the same. There we go, and the graph looks the same. So I think everything was fine with that. And then maybe I have a few more minutes here. Yeah, so let's read to the graph, and then that'll be it. The resulting maximum log length in our dataset is 208. It is useful to visualize a histogram of the length distribution because it will help us to make a more informed decision on where to cut the line. The following graph shows that most of the logs are concentrated around the 130-140 byte length, and there are some peaks at 160, 190-ish, and some at the 208 boundary. In this case, I will not be doing any filtering, but this is something you may need to do if you have a low number of exceptionally large logs. They would cause your whole model to be much larger and complex because you will need to build long matrices for each log. There has to be a balance between how much information is lost if we drop those logs and how worse the overall training result will be if we keep those logs, as a result of having much larger matrices. There is no good response to this question, and testing will be the only answer. So that's a great stopping point, and we've got the notebook that's running locally on my machine matching what the author has here. So this is a great place to stop. So thanks for watching, and see you in the next one.